Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Nonlinear effects are what happens when waves on the beach crest and crash, says Keefe Mitman, a Caltech graduate student who works with Saul Teukolsky, PhD 74, the Robinson Professor of Theoretical Astrophysics at Caltech with a joint appointment at Cornell University. The waves interact and influence each other rather than ride along by themselves. With something as violent as a black hole merger, we expected these effects but had not seen them in our models until now. New methods for extracting the waveforms from our simulations have made it possible to see the nonlinearities. The research, published in the journal Physical Review Letters, come from a team of researchers at Caltech, Columbia University, University of Mississippi, Cornell University, and the Max. In the future, the new model can be used to learn more about the actual black hole collisions that have been routinely observed by LIGO, Laser Interferometer Gravitational Wave Observatory, ever since it made history in 2015 with the first direct detection of gravitational waves from space. LIGO will turn back on later this year after getting a set of upgrades that will make the detectors even more sensitive to gravitational waves than before. Mitman and his colleagues are part of a team called the Simulating Extreme Spacetimes Collaboration, or SXS. Founded by Teukolsky in collaboration with Nobel laureate Kip Thorne, BS 62, Richard P. Feynman Professor of Theoretical Physics, Emeritus, at Caltech, the SXS project uses supercomputers to simulate black hole mergers. The supercomputers model how the black holes evolve as they spiral together and merge using the equations of Albert Einstein's general theory of relativity. In fact, Teukolsky was the first to understand how to use these relativity equations to model the ring-down phase of the black hole collision, which occurs right after the two massive bodies have merged. Supercomputers are needed to carry out an accurate calculation of the entire signal, the inspiral of the two orbiting black holes, their merger, and the settling down to a single quiescent remnant black hole, Teukolsky says. The linear treatment of the settling down phase was the subject of my PhD thesis under Kip quite a while ago. The new nonlinear treatment of this phase will allow more accurate modeling of the waves and eventually new tests of whether general relativity is, in fact, the correct theory of gravity for black holes. The SXS simulations have proved instrumental in identifying and characterizing the nearly 100. This new study represents the first time that the team has identified nonlinear effects in simulations of the ring-down phase. Imagine there are two people on a trampoline, Mitman says. If they jump gently, they shouldn't influence the other person that much. That's what happens when we say a theory is linear. But if one person starts bouncing with more energy, then the trampoline will distort, and the other person will start to feel their influence. This is what we mean by nonlinear. The two people on the trampoline experience new oscillations because of the presence and influence of the other person. In gravitational terms, this means that the simulations produce new types of waves. If you dig deeper under the large waves, you will find an additional new wave with a unique frequency, Mitman says. In the big picture, these new simulations will help researchers to better characterize future black hole collisions observed by LIGO and to better test Einstein's general theory of relativity. Says co-author Macarena Lagos of Columbia University. This is a big step in preparing us for the next phase of gravitational wave detection, which will deepen our understanding of gravity in these incredible phenomena taking place in the far reaches of the cosmos. Thanks for watching. Please subscribe my channel for more videos.